Okay, so here we go again with some normal distributions. When we're talking about data, it says our student outcome today is to calculate z-scores, use technology and tables to estimate the area under a normal curve, and students interpret probabilities in the context. Now, today is just normal distributions, and that's how it is easier. If you remember in the last lesson, I talked about it's much easier to find standard deviation, that type of stuff whenever we're talking about normal distributions. So lesson notes, it says, in this lesson, students calculate z-scores and use technology and tables to estimate the area under a normal curve. Depending on technology resources available to students, teachers may need to have students work with a partner or in a small group. So you're going to need to get together with people that have the same calculator as you and figure out how to do this on your own calculator. I'm going to give you a demonstration on Desmos, whichever one of you can use, but it's better for you to be able to use it with your own calculator to get familiar with your own tools. So let's go to the whiteboard. This says consider the following data distributions. In the previous lesson, you distinguished between distributions that were approximately normal and those that were not. For each of the following distributions, indicate if it is approximately normal, skewed, or neither, and explain your choice. Let me get this a little bit smaller here so we can look at it better. Okay, so for the first one, this right here is very normal, okay? And we would say it's normal because it's a mound shape. Okay, it looks like a big mountain, big hill, okay? Same thing for this one, even though it's a little bit more spread out, it's still mound shape. So we're going to call it normal and mound. That's the explanation. Now if you look at C, well, that's definitely not the mound that we're thinking of, and so we would call this skewed. So not normal, and it's skewed to the right. Remember I said whichever way you slide off of the slide, climb up this way, and you're sliding down this way, so that would be skewed right. And that's very hard to determine the percentage under the curve, okay? Now, this one is pretty much mound shape, so we would say this is normal. Normal distribution. What that means is it's distributed evenly. Okay, this is not distributed evenly. It's very heavy to the left side. These are all distributed fairly even. Okay, so it's distributed. The data is spread out pretty even. Okay, so it's normal distribution, and once again, it's mound shaped. Now, although this looks like it's kind of evenly distributed, it's not really a mound, right? This would be kind of like it's more like a plateau, right? This is, I'm not sure if I spelled that right, but it's kind of plateau, so it is not normal, okay? It's still very hard to determine standard deviations under that. So what we're looking for in a normal distribution is a distribution that has a particular symmetric mound shape, just like this. Of course, it can be flat or not as tall, but as long as it's mound shape, everything should be okay. Okay, so that is normal distributions. Okay. Now we're going to talk about our z-scores and calculating the probabilities. So when calculating probabilities associated with normal distributions, z-scores are used. A z-score for a particular value measures the number of standard deviations away from the mean. Okay, so if you give me any value, I can tell you what the standard deviation is away from the mean. So a positive z-score corresponds to a value that is above the mean. A negative z-score, of course, would be below the mean. The letter z is used to represent a variable that has a normal or a standard normal distribution where the mean is 0 and the standard deviation is 1. Okay, so whenever you're looking at a mound shape, the mean, count that as 0. This one above and below, that would be 1 standard deviation between. Okay. The distribution is, this distribution was used to define a z-score. A z-score is calculated. So here's your formula to find a z-score. Whatever value you're looking at minus the mean divided by the standard deviation. Okay. Now, I'm not talking about standard deviation 1, 2, 3 whenever we're looking at it on the graph. It's what do we calculate the standard deviation to be. Okay. If the typical value away from the mean is 50, then that's your standard deviation. All right, let's look at A. This is the prices of printers in a store has a mean of $240 and a standard deviation of $50. The printer that you eventually chose costs $340. What is the z-score for the price of your printer? So really what you're looking at here is, am I getting ripped off by paying $340 for a printer? If the mean, the average printer is $240, is $340 way too high? So I says, what is the z-score for the price of your printer? Well, we were given the value of our printer. It was $240. We're also given them, oh no, I'm sorry, that is incorrect. The value was $340. The mean is $240. And then we divide by the standard deviation. Well, what is 340 minus 240? That is equal to 100 divided by 50 is equal to 2. So you're at 2 standard deviations. Okay, so you're down inside that 1 standard deviation range. Of course, about 68% of your typical printer values are going to be. You are all the way out into the 95% range. Okay, so how many standard deviations above the mean was the printer? Well, that is 2 because it's positive. It's a positive 2. That means it's above the mean. Let's look at page 4. This says, Ashishi's height is 63 inches. The mean height for boys at his school is 68.1 inches. And the standard deviation of the boy's height is 2.8 inches. What is the z-score? So what is our value? 63. What is the mean? 68.1. And what is the standard deviation? 2.8. So if you were to calculate that, this is a negative 5.1 over 2.8. It ends up equaling about a negative 1.82. So what is the mean? What is the meaning of this value? Okay, well, since it's negative, it means we are below the mean. And we're below it by a standard deviation of 1.82. So what does that mean for this kid? Oops. Well, it means that he is still within the 2 range, right? Because it's more than 1, but it's less than 2. So he is right in with the, if you were to have, that's not a real good mound. If this is the mean, there's 1 standard deviation. I'll do the scribble for the 2 standard deviations. He would be down in here, right? He would be almost up to 2. Okay. Or he'd be almost up to 3. He'd be almost all the way into the 3rd standard deviation. Okay. So, explain how a z-score is useful in describing data. Well, a z-score tells you how far you are away from the mean. Okay. We're a long ways off the mean if we're all the way up to 2. Okay. And we know that because this is where this is where 90 or 68% fall. Okay. 68% of your typical values fall within this range. Well, you're into the second portion here, so that's where only 95, so you're well below the mean here. Now let's go to page 5. It says a swimmer named Amy specializes in the 50-meter backstroke. In competition, her mean time for the event is 39.7 seconds. The standard deviation of her times is 2.3 seconds. Assume that Amy's times are approximately normally distributed. That's the key here. We have to do approximately normally distributed. Okay? So, what is her value here? Estimate the probability that Amy's time is between 37 and 44 seconds. Well, you've already said that the mean is 39.7 and a standard deviation of 2.3 seconds. So that's going to take care of the 37, but it's going to be a little bit outside. Your 44 seconds is going to be a little bit higher than your standard deviation. Okay, so we're going to estimate what's the probability that she falls within this range. Okay, so let's start with 37, and we're going to subtract the mean, which is 39.7, and we're going to divide by 2.3. So that's going to be a negative 2.7 over 2.3, which is about 1.17 negative. Now, if we go to 44, because that's the upper end of the range, we're going to subtract the mean, divide by the 2.3, and this is going to equal 4.3 over 2.3, which is about 2. We're just rounding it to about 2 there. So if we are to combine these now, because this is how far she is below the mean when we're talking about the 37, and if we're talking about the 44, she's above by 2. So if we combine those, we really don't care about this being the negative other than the fact that it's on the other side of the mean. So if we were to combine these, let's say 1.17 plus 2, she has a range of 3 standard deviations. She's reaching all the way down into the 1.17 here and the 2 standard deviations here. Okay, so what is the probability that she's going to be in there, in that range of 37 to 44? Well, we're going to be able to figure it out by looking at a z-scores table or plugging that into our computer. Okay, so here is our graph and our normal distribution, and notice that the comma here is separating the mean and the standard deviation. So we type in 39.7 because that's the mean, with a standard deviation of 2.3, and this gives us our curve. And it says finally cumulative probability. And so I typed in 37 to 44 because that was the seconds that we were talking about. So what is the probability that it will land in between 37 seconds and 44 seconds her next race? Well, that's 85% or 0.849, blah, blah. And if you look at the graph here, that's in between these two, or the highlighted region here is what it's talking about. Remember that it was only negative 1.17, and over here it was all the way down to the 2. So that's the reason why there's more shaded on the right side than on the left side, because this only went to 1.17. Okay. So there's how you can see that in Desmos, or you need to be able to do this in your own calculator. You should be able to go to the graphing or into the statistics functions and type these in somehow. All right. So this says using z-scores and a graphing calculator. Well, we just did the z-scores with a graphing calculator, and we said it was going to be about 0.85 or 85%. Okay. Now, estimate the probability that Amy's time is more than 45 seconds. Well, if we go back to Desmos here, and we want to go more than 45 seconds, okay, there's our curve, and you can't even see it really, but if you zoom in right here, what's the probability that it's going to be more than 45 seconds? Well, there's only a 0.01 chance. Okay? So, we can go back here and say that it's only going to be a 0.01% probability. Now, if we go to D, using z-scores and graph calculator, round your answer to the probability that our time in our next race is more than 45 seconds. Well, to talk about it being more than 45 seconds, we would have to say the value of 45 minus the mean, which is 39.7, over the standard deviation was calculated to be 2.3. Now, if you did this, you would get 5.3 divided by 2.3, which is about 2.304. So now, what does that mean? That means that's not her probability, but that is where she's at on the standard deviations. So if we go back to our Desmos and we look at it again here, we're going to have the only chance that she's going to be above the 45 is still 0.01. So that tells us that 0.01 is at the standard deviation of 2.3. Okay? That's the standard deviation. Okay? Let's go to page 6. Now, E says, what is the probability that Amy's time would be at least 45 seconds? Okay? Well, if it's going to be at least, that means she's got to have more than 45 seconds, right? 45 seconds or more, so it'd be the same thing. So it would be 0.01, I think it was like 1 or something like that if we rounded it. So the odds of her being higher than 45 are not good, which is good for her. She wants the quickest score, right, in a swim meet. So that's good. Elf says using z-scores and a graphing calculator and rounding your answer to the nearest thousandths, find the probability that Amy's time in her next race is less than 36 seconds. Well, hopefully you're used to this. We're going to take the value, subtract the mean, divide by the standard deviation. So this is going to be a negative 3.7 over 2.3. That's going to be a negative 1.609 Okay. So that's rounded to the nearest thousandths, and that tells us that it's going to be below the mean, which is good. And we also have to find the probability that it's going to be less than 36 seconds. So we're going to come back here. Notice on these that I do to positive infinity and to negative infinity as the minimums and the maximums. And then the max, because we want less than 36 seconds, right? Less than. This is more than 45 seconds. Less than. So if we graph this, we're going to have to slide to this side of the mean because we're below it. And there is the chance of being below 36 seconds is only going to be 0.05. So not a good likelihood that she's going to be able to race under a 36-second time. Okay, let's do another one right quick. Talking about the distribution of lifetime of a particular brand of car tires has a mean of 51,200 miles and a standard deviation of 8,200 miles. Assuming that the distribution of lifetime is approximately normally distributed and rounding your answers to the nearest thousands, find the probability of each event. So to find the probability, we have to find how far away it is from the mean, or from the mean. Okay, how many standard deviation, and then we have to figure out the probability inside that standard deviation. So a randomly selected tire lasts between 55,000 and 65,000 miles. So we're finding in between two different mileage here. So first we're going to find the first mileage of 55,000 minus the value minus the mean divided by the standard deviation. And go ahead, while you've got that in your mind, write the other one, the value of 65,000 minus 51,200. And then you're going to divide that by the standard deviation. Now, whenever you do that, you're going to get how far away it is from the mean. Now, that's not the probability, that's just how far away it is from the mean. So I'm going to calculate that, and you will get 0.463, and if you do this one, you get 1.683. Okay, so what we're looking at here is we know that the mean is 51,200. 55,000 is 0.463 away. And then 65,000 is 1.683 away from the mean. But all we're going to be looking at is what goes in between this. Okay, so I've already got that done on Desmos. Let's come up here, let me find it. Right here. The normal distribution with a mean of 51,200 and the standard deviation of 8,200. You're going to find the cumulative, which means the combined probability of the values of a minimum of 55,000 and a maximum of 65,000. And when you do that, let me graph it for you. There it is. That's kind of what I was showing you under that curve a while ago. That's only the values that you're looking at, and the probability of falling in between that range is 0.275. So let's write that, and we'll write it 0.275, which we would say is about 28% chance. Okay, when we talk about probability as a percentage. Okay, now randomly selected tire lasts 48,000 miles, at or I'm sorry, it says a randomly selected tire lasts less than 48,000 miles. So we already know that this is 51,200. 48 is going to be somewhere right in here, right? And we're talking about all this down through here. Okay? So you should be able to make a guess. It's going to be less than 50%, right? But how much? We don't know. So let's figure it out. Now, if I said my value is 48,000 minus the mean divided by the standard deviation, that ends up being a negative 0.390. Remember, the negative tells us that it's to the left of the mean. So if we go and calculate that, take that off, here we are, less than, meaning everything to the left of 48,000. If I plot that, that's what it looks like, pretty close to what I freehanded earlier. And that's going to be 0.348. So that's the chances. 0.348. That's the probability that you're going to find a tire that's less than 48,000 miles. It lasts less than 48,000 miles. Okay, let's scoot over here. Now, same thing. A randomly selected tire lasts at least 41,000 miles. So this is going to be everything above 41,000 miles. Let's go ahead and calculate it. Now this one is also going to be a negative number, but that doesn't always mean it's going to be less than, it's not always going to be less than 50%, and I'll show you why. Because if you draw this curve here, this is our 51,200, 4,100's over here. That's negative 1.2 standard deviations away, but we're talking about it has to be at least, so it's going to be everything to the right of that value. Okay, so it's going to be greater than 75% probably. Okay, so let me erase that, and let's go to Desmos. And let's calculate it. Let's look at it. There you go. And it's 0.893. I'll show you that one more time down here. Here's the the minimum is 41,000. We're going to the maximum, and that is 0.893. 0.893. So you got a really good chance of picking a tire at random that's going to last you at least 41,000 miles. Okay. Now it says explain the meaning of the probability that you found in part A3. So in this one, whoops. That one right there. So what that means is that the probability of randomly selecting a tire that lasts more than 41,000 miles is 89.3% chance. And now that is of this brand, right? Okay, hopefully you understand all that. Let's keep going. Now, this says, exercise 4, think again about the brand of tires described in exercise 3. What is the probability that the lifetime of a randomly selected tire is within 10,000 miles of the mean lifetime for tires of this brand? Okay, so to figure that out, we would have to say, we would calculate it as to the left and to the right. So our mean was, our mean was 51,200. So that would mean our, to the left of that would be 41,200 over 8,200. And then the other one's going to be 61,200 minus 51,200 over 8,200. Now, when you calculate that, this one is going to be about a negative 1.22. This will be a positive 1.22. Let me see if I did this on Desmos, I don't remember. Okay, yeah, I did. So here it is. To be within 10,000 of each of the mile, you would have about a 78% chance there, if you see that right there. Minimum of 41,200, maximum of 61,200. You got about a 78% chance. So let's write that. You have about a 78% chance. Now, page 9. All right, so this says the normal distribution, the standard normal distribution is normally distributed with a mean of 100 and a standard deviation of 1. The diagram below shows standard normal distribution curves. Use a table of standard normal curve areas to determine the shaded areas. So what that is, that's called a Z-score chart. And so if you look at this, this is what a Z-score chart looks like. You have your Z's. So if you needed, well, I'll just show you here. We need a 1.23. So we would come down here to the 1.2, over to the 0.3, 1.2, and then there's the 0.3, so that's the 1.23. And you see that to be 8907. Now, what these Z-scores are, these are values to the left of the Z-score. So if you look back at our chart, that's what we need. We need the probability of the values to the left right here, which is exactly what we had, and it was 0.8907. Okay? Now, when you come down here to the negative 1.86, we need to think about it for a second. If it's normally distributed, and this is the plus 1.86, are there any more values, or is there a difference in the values if we were looking from here to the left, or from simply, let me go with a different color here, or from here all the way to the right? No, there's no difference. So even though this is a Z-score chart that goes to the left, when you're not taking anything out like you are over here on C, see how these are different? It's not just all the values to the left or to the right. That's the difference. That's when it becomes a difference. Here, all we have to do is look at our 1.86. So 1.8 is here. Now let's go over to the 6. So 1.86 is 0.9686. So that is our value, 0.9686. Okay? Even though that's negative, it doesn't matter because we're just talking about the probability or the values that are inside that curve. Okay? Now, here's where to get a little tricky. Here we're looking for negative 1 to 2. So first let's start on the right side because that's what we have. The 2, our Z-score tells us the probability for everything to the left of 2 right here. Here's 2.0, everything to the left is 0.9772. Okay, so let's write that up here. 0.9772. Okay? Now, that is all the values here, including this down here. But that's not what we want. Okay? we're going to have to stop at -1. So how are we going to figure that out? Especially when our Z chart is telling us all the values to the left. How am I going to figure out the values to the left when there's not any there? Okay, well, what I'm going to do is look at my chart for 1. Right here it is for 1.0. It is 8413. 8413. Now, if I take that and I subtract that from 1, okay, that will give me all the values to the left of 1. Okay, because this is -1. That will give us all the values to the left of -1. So when you subtract that, you actually get, let me make that make sense. Okay, so let's just do it. I'll put it up here. If we, let's do some subtracting, okay? Now, what do we have to do? We have to make that a 0, make that a 10. So I have to make that a 9, make that a 10, make that a 9, make that a 10, make that a 9, make that a 10, okay? Now, we can do this. We would get a 7, 9 minus 1 is 8, 9 minus 4 is, I'm sorry, that's 9 minus 4 is 5, and then you would get 9 minus 8 is 1, okay? So then we're going to take that up here and subtract it, and that's going to give us our total value of 0.8185. That is the total value of the probability of values that fall in this range here. That's the reason why it's a little bit more difficult using a z-scores chart, because you got to take into account that that's only talking about, because you can imagine if you had all the values of to the left and to the right, that's just a humongous chart. It would take too long to be able to figure all that stuff out. So it just gives you all the ones to the left, and you have to figure out the others.